In SAC 104 number 6, you got somebody has a pair of blocks attached to each other by a spring on a flat horizontal surface. She pulls the blocks apart and releases them from rest. They go flying toward each other. The spring decompresses, it shortens, and at a particular instant, while the spring is still at least somewhat stretched, we've got block number 1 moving toward block number 2 with a speed of v1 prime. They want to know how much the spring is stretched at that instant. Well, let's draw a before and an after picture. We use the instant after she lets go of it, so the person is no longer interacting with the system, for our before instant. We've got the spring stretched out in between the two blocks. By some amount, I'll call it x, where the spring would only be this long, L0, if it wasn't stretched at all. Okay, and the blocks start moving together. We choose an after instant. And of course, I'm going to pick the after instant to be that instant when the speed is v1 prime, since they're asking us about that instant. The blocks are closer together. But the spring is still stretched, just not as much. So I'll call this, this looks like the same distance that I drew in the last diagram. That'll be that's how long it would be if it wasn't stretched at all. And now it's stretched less than it was before, a distance that I'll call x prime. And in the after picture, the blocks are moving. There's the given v1 prime and v2 prime. Now, we're looking for this, x prime, but we don't know this. So I would think we just use conservation of energy if we knew v2 prime. Energy before equal energy after. It would be all spring potential energy here and a mix of potential and kinetic energy here, and the spring potential energy would depend on x prime, which is what I'm looking for. But I don't know v2 prime. However, there are no, since she let go of it, there's been no outside influence on the blocks on any part of the system. It's just different parts of the system acting on each other. So we can apply conservation of momentum. Let's try that, see what that gets us. I think that'll get us v2 prime, and then we can use the conservation of energy to find out what x prime is. So we'll go sum of the momenta to the right. I'll call it to the right positive. The subscript means the arrow shaft means I'm summing along the horizontal, the right left, and the arrow tells you that I'm calling to the right positive, which means by default that to the left is negative for momenta. So that's going to be equal to some of the momenta in the after picture, and I'll use primes to designate after. Well, here nothing's moving, so the momentum's got to be 0. In the after picture, I've got m1 moving to the right, so I have m1 v1 prime, plus I've got m2 moving to the left. That'll be a minus m2 v2 prime. And of course, we can leave that plus sign out if we want. I think I'll do that and just say it's m1 v1 prime minus m2 v2 prime. Alright, solve that for v2 prime. And I've got a handy expression. Now, all this stuff, v2 prime is now known, so in terms of all this stuff, x prime is the only thing that's unknown, and I should be able to get that using conservation of energy. Let's try that. We'll go E is equal to E prime, meaning the energy in the before picture is equal to the energy in the after picture. I'm using primes for after, unprimed before. The energy in the before picture, well, let's, at most, the mechanical energy that I'm keeping track of could be the K, kinetic energy of object 1, plus kinetic energy of object number 2, plus the energy stored in the spring in the before picture. And that'll be equal to the same stuff in the after picture, but I'll put primes on it, so we're talking about after picture. Now, what's 0 here? Alright, object number 1 is not moving in the before picture, so the initial kinetic energy, that's kinetic energy of motion, is 0 for object 1. Object 2 is not moving, same thing, 0. The spring is stretched in the before picture. So objects aren't moving, but the spring is stretched in the before picture. In the after picture, I got both objects moving, so both of them have kinetic energy, and the spring is still stretched somewhat. So the energy stored in a spring is 1/2 k x squared. Here I get a lowercase k. This is the spring constant, how stiff the spring is, also known as the force constant of the spring. Make sure you don't confuse that with the uppercase k for kinetic energy occurring in this same problem. It's important to make it so that the reader can tell you your cases apart. So we got 1/2 m1 v1 prime squared is the kinetic energy of block 1 plus 1/2 m2 v2 prime squared for block 2 plus the 1/2 k x prime squared for the spring potential energy in the after picture. So, well, we've got this v2 prime in here, which was not given, but we've solved for it. Let's do substitution. This is what we mean by pure substitution when we're dealing with an algebraic expression. I just pop that thing in there, the right-hand side, as is, right where I see v2 prime, without any other algebraic manipulation occurring during the same step. So the left side stays the same, first term over here stays the same, everything else but that v2 prime squared part stays the same. So I've got this thing in parentheses squared with the v2 prime, and it's m1 over m2 times v1 prime. And then plus this term stays the same. Okay, now I can start solving for, I'm going for x prime. I think I'm going to simplify this term a little bit. Hey, what do you say we multiply by 2 on both sides? Every term on this side has a 1/2 in it. That makes the 1/2 go away. I think I'd like to combine these and simplify it a little bit before I divide both sides by the k and take the square root. So I got kx squared equals, let's see, what's both of them have an m1 v1 prime squared in it, so I'll factor that out. Of these two terms, so I got m1 v1 prime squared times, this is just multiplied by 1, because that's the whole term. This, there's a v1 prime squared, so that's already taken care of. And then I've got m1 squared over m2 squared times m2. That'll give me m1 squared over m2, except I'm taking the m1 out. We've got to get one of those m1s out, so that erases the squared there. And that's good. I can add two numbers that are both pure numbers. Neither one of them's a mass now, so this expression makes sense dimensionally, in terms of units. That's what dimensionally means. And then kx prime squared. Alright, I'm solving for the x prime squared, so, well, for the x prime, but I want to get that all by itself. So I'm going to subtract this piece from both sides, and I'm going to switch sides. So it would leave kx prime squared on the right, but I'm switching sides, so I got kx prime squared on the left, and then what was originally on the left is the kx squared minus this piece that I subtracted from both sides, which I feel like writing as in this way. Just switch the order around a little bit. You can do that with multiplication. And then I'll have x1 prime squared is equal to, just divide both sides by k, x squared minus, and I'm going to write this as m1 over k, and I changed my mind on the order, so I got m1 over k times 1 plus m1 over m2 times v1 prime squared, having divided both sides by k. Now I'll take the square root of both sides. I'm going to do that. Use the pencil method, erase the square on that side, and apply the square root to this side. And that represents my answer for the whole problem. It'll be x prime. Can make sure I was given the two masses. I know I was given v1 prime, I remember that. Make sure I'm given the two masses, the spring constant, and the amount it was stretched originally. So, two masses, the spring constant, and I do remember they gave me the amount to x. So I've got nothing in my answer but givens. That's definitely okay. I want to check out the units. The units will save my bacon if I get some algebraic mistake. I want this term over here to have units of meters squared. This has units of meters squared, and I can add meters squared to it, and of course take the square root, I get meters, which is what an amount of stretch is going to have. So as long as this term right here has units of meters squared, I'm okay. So I'm just going to work on the units for that one. That's kilograms divided by the force constant. This has units of force per stretch. That's newtons per meter. Now, instead of putting the per meter down here, a reciprocal in the denominator is the same thing as what was the denominator up here in the numerator, or multiply top and bottom by meters if you wish. This has no units whatsoever, and then this I have units of meters squared per second squared. It's meters per second all squared. The newtons, let's go ahead and write out what a newton is. I'm going to scratch that and replace it with what it is. It's a kilogram meter per second squared. At this stage you might just have to look that up. Okay, in the denominator, when I multiply these two denominators together, these parentheses are actually important here. Multiply the two denominators together and the seconds will cancel. And then these meters cancel. These kilograms cancel. And I got meters squared left, which is just what I wanted. I wanted to prove that this term had meters squared, because then I got meters squared minus some value of meters squared gives me a value of meters squared. Take the square root of that. And I just got to hope that this piece is less than 0. I can't prove that right now in any easy fashion, but this will turn out to be less than 0 if we had values, and confident that since the units work out, we've got the appropriate answer. We've got the correct expression for x prime, the amount by which the spring is still compressed in the after picture. That does it for SAC 104.